Good morning and welcome everyone to Engineering Tomorrow's Robotics Special Lab event. We're so happy to have you guys here with us today. I hope you're ready to put those coding skills to the test and hear from some experts in the field and just have a lot of fun with us, okay? We do ask that you remain on mute throughout the engineer's introduction, but don't worry, there will be lots of opportunity for engagement throughout the day, all right? So with that, I have the pleasure of turning this over to our incredible engineer presenter, Mr. Pat Marshall.
Good morning, everybody. I know it's been a cold trip for many of us. I know my drive was at an average of -7 when I got up and arrived at school today. So thanks for getting out here and trying to make it all work. So hopefully, as you roll in, we're going to engage you in something I find very interesting and one that is involved in all sorts of engineering disciplines. And robotics is the topic today. And we're going to be focusing on the coding aspect of robotics because really that's what controls what they do. And we're going to look into where we use them, why we use them, how the code is going to engage with a robot that is trying to perform a certain task. And so I'm excited that you guys are here. I know whether you're a mild expert in coding, you've seen it before, or this is the first time, I hope this is an exciting introduction into that world. First, let's take a look at those that have been involved in this lab that have done a lot to make it work, and it's a potpourri of engineers with many years of experience to college mentors that are at the forefront of the technology itself and really have blended together to make this a really wonderful, engaging lab. And our hope is that not only are we providing you with some variety of levels when it comes to learning how to code, but also seeing where it's applied in the professional world out there. And so that's the goal of whenever we do one of these labs, to give you both ends of that spectrum. So thanks to everybody on the screen that's involved with this development. It's hours and hours of work throughout the year to make something like this work. Let's go here. So a little bit about me. My background is civil engineering at the University of Illinois. And I've done a variety of things since then, building footbridges in Lesotho and in the Peace Corps. As a high school teacher, I've taught physics, computer science, engineering, and aerospace, and been a part of a variety of teams, including robotics teams. So I've done a lot of work with all sorts of different codes and robots and things like that, and it's very much an interest of mine and something I love to talk about. So hopefully we can get you excited about this kind of thing today. So one of the first things I think about is, what is the purpose of code? So for those that are here, I'd like you to maybe just close your eyes and think about where you're at in whatever room you're at. And just if you close your eyes and think right now, without opening your eyes, how do you get to a door and get out of that room? And you can never open your eyes. First thing you might do is kind of reach out and see what's ahead in front of you, right? And you might see something, feel something, turn, move, bump into stuff. And you might do it in a very calculated manner, or you might do it in a random manner, right? That could be very painful, and a lot of bruises might result from that. But there's a lot of things in your way. And so what would you do to help get through that maze of objects that you just sat next to, but maybe you forgot where things are or how far they are? And so you would need instructions. And so you might have a friend dictate to you how to get out of that room. But sometimes those instructions may not be as clear as you think they might be. And so that's something we want to work on, is that robots need your instructions to be clear and very concise. Otherwise, it might take a while to accomplish the task that you're trying to accomplish. I think about the New Horizons probe sometimes, and when I talk about space, and if we sent this probe out to Pluto back in 2006, and and I'll put it here, traveling at 10 miles per second. Just think about that for a moment. That speed leaving the Earth, 10 miles per second, it took a year to get to Pluto. But not only that, if you want that probe to do something, to accomplish something for you, and NASA has a lot of ideas, they have a lot of things on that probe they wanted to get done. how would you communicate with it? You know, you're not sitting in front of your PlayStation and controlling whatever's happening in the game and, you know, doing it immediately, right? The response time is different. And so what I'd like you to do is think, for those that can, answer this question. If you can join Slido right now and you see the number shown, there are questions there that will hopefully give you an idea for how long would it take to communicate with the probe that's all the way out there. And so I'm going to think it's on. So here we go. So jump on in. What do you think? How long, if you said turn right, how long would it take for that, and right's a kind of a vague term out in space, but you know, to roll, to pitch, and to yaw, to move and change anything about what that probe is doing, how long would it take to communicate? And we got a couple of answers here. 4 hours, 8 hours, think about it. And I purposefully put a picture of an electromagnetic wave on there to maybe inspire you to think, well, how are we communicating with that probe? And so we have answers that are jumping around on us a little bit. I love it. All right. You know, it's hard to imagine, but it would take approximately 4 hours just to send the signal and another 4 hours to receive that signal back saying, yep, I did what you wanted me to do. That's a whole workday. And so the idea, and you guys are getting it right in terms of approximate hours. It wouldn't take a whole day, but if you've ever seen the movie The Martian, when they sent messages out to Mr. Wahlberg, who was stuck on Mars, you know, you'd send something, it'd take 20 minutes. And so to go out to Pluto, it's a long time. And so you cannot think that you're going to sit at NASA and just use a joystick and control it. You have to have some automation. And that is the point of what we're trying to get to today, is you have to set something up and make sure that when it gets to where it needs to be, that robot, that probe will do what it needs to do to acquire the data that you want. We're in stacks. In fact, NASA is still communicating with the Voyager probe that was sent out almost 40 years ago. They changed some lines of code to make sure it worked properly and updated it a little bit, and is still sending signals back. So it's amazing what a good chunk of code will do to keep that robot running. Okay, so thank you for jumping in on the Slido. I'm going to stop the Slido right now, and I want to get into trying to advance. Oh, wait, go here. I'm not sure if you saw that. Okay. So this is also something I wanted to show you very quickly, and that is, this is a sensor bot that I built for my class. And I'm going to mute it because it's kind of an annoying humming sound, but you'll see it follow a line. Again, something that we're going to ask you to do today. We'll mute it. But you can see that there's a line file, there's sensors underneath that detect whether it's hitting a white line or not. And so what would you do to make sure that, you know, it responded correctly and properly to following something like that? Or in the sense of what you're going to do today, maybe a black line that's on the screen. So sensors and getting feedback is one of the things that we will work on when it comes to the code. So I want to show you a quick video. Sorry, I'm trying to get through these slides about what engineers make robots. What type of engineer do you need to be? And so let's listen here, and then I'll give you some insight into some of the skills that you may need to make robots.
My name is Tessa Lau. I am Chief Robot Whisperer at Saviok. Saviok is a robotics company, and we're building autonomous robot helpers for the services industry. I went to Cornell for my undergrad. I got a bachelor's in applied physics and computer science. I really liked physics because it was about hands-on doing experiments and building things and making stuff real. Computer science was also really interesting because you could create stuff a lot faster on a computer. And so I went into computer science for my graduate studies. I went to University of Washington, where I studied artificial intelligence and human-computer interaction. I don't think of myself as a roboticist, even though that's what I do. Robot whispering for me is about making it so that the robots behave well in human environments. And it's not just about programming or engineering, it's about looking at those robots in context. The way he's being used is that the front desk receives a call from a guest room saying, I'd like to order a sandwich, or I forgot my toothbrush. And so they grab the item that they want to deliver, load it into the robot, type in the room number, and the robot will go off to the room automatically. Robotics has the potential to actually change people's lives in a much deeper, fundamental way than software could, because robots are physical. They can actually move around in your world and do things for you. The robots that we are building, they can't replace a human because there's so much that a human can do that a robot can't. What they can do is the mundane stuff that no one wants to do anyway, like, run stuff up to a hotel room and then come back down. No one person can build a robot on their own, and we all know that, and we all help each other out. I think one of the biggest skills that I bring to Savioke is soft leadership skills. I'm invested in making sure everyone's working together. I think it's really valuable to know a lot about a variety of things and then have a specialty within there where you focus and do a deep dive. I know computers, I know networking, I know physics, and that actually gives me knowledge about mechanical performance and just the basics of electrical engineering. I do a lot of integration testing, just making sure all of our software works properly on the physical hardware. We use GitHub a lot, which is an online collaboration tool for sharing source code and commenting on it. We're leveraging a lot of the contributions from the open source community. Those tools are freely available. Anyone can pick them up and learn how to use them. My advice to women going into STEM field is don't listen to anyone who says you can't do something. Definitely cultivate hobbies related to the field that you want to be in. I was lucky that my dad was into hobby computers, and so he brought one home, and so I would spend a lot of time just playing around with the computer and seeing what it could do. We have those robots out in hotels right now. We can log into them over the internet and watch them as they're doing deliveries to hotel guests. Seeing the people interact with them and be delighted, all of those interactions are happening because of things that I built, and that's really incredible.
So you can see here that there is a lot of skill sets that go into it. But one of the things I want to ask of you as a group is think about, what does a robot have to do to really be productive? What does it need to, there's inputs and outputs, but what are the major things that a robot needs to have in order to kind of get from point A to point B? And so if you thought about this, they're kind of, hang on, let me get out of this. We can think about, what can a robot do? And, can cook and perform surgery, very precise surgery, which is something that many talented doctors out there that can do. But if you have a robot assisting you in the process, that can be a wonderful thing. Folding laundry, like not many of us want to fold laundry. And if you have some robot doing it, I think that'd be wonderful, right? And so doing things that maybe we don't want to do on a daily basis, but we want done like repeatedly and accurately, that can be a great use for a robot. And so there's another video I'd like to show you that is a really cool video about, how robots are coded and how they might function, like how they work and the main parts of it. Like as a human, we interact with the world with our brain and our senses. And so robots need to have a similar set of things to be able to take input and output and operate. So let's take a look.
Someday in the near future, you might be wandering around town at night when out of the blue, you'll stumble across a robot. If that happens, maybe you shouldn't be too surprised. Not so long ago, robots were mostly found in the realms of science fiction. Today, they're vacuuming floors, building cars, and even roaming around the surface of Mars. Robots are still pretty far from having a human-level capacity of intelligence, or even dexterity for that matter, but they're already a big part of many branches of engineering. In the US, over 100,000 robots have been added to factory floors since 2010. Knowing exactly what robots are, what they can do, and how they work is more important than you might think, because soon they might be living among us. The classic picture of a robot is something with human-like intelligence and maybe even a humanoid appearance. But like so much else, real-life robots aren't much like what you usually see on TV. Robots come in all shapes and sizes, and they can be built very differently depending on what they're used for. For example, some of the robots used in mining are made from a camera mounted on a small chassis with wheels. That allows them to enter and inspect mine shafts and even retrieve leftover material from places it's hard to get people in and out of. Meanwhile, in medicine, specialised robotic arms, with a bit of human assistance, can perform precise surgeries through the tiniest incisions. There's also a difference between robotics and artificial intelligence, or AI, which people sometimes confuse. While some of the concepts are similar, robotics deals with a specific set of ideas, although it does borrow a few from AI. AI deals broadly with the goal of automating decision-making for complex tasks, the kind you can't write a simple set of rules for. That could be everything from playing chess to driving cars. Right now, AI systems tend to have very narrow goals, but the holy grail of AI is to develop a system that can make intelligent decisions about any sort of task using different sources of information. Our focus will be on robots which are designed for more specific purposes in the physical world. In engineering terms, a robot is a machine designed to interact with its environment, make an appropriate decision based on those surroundings, and then carry out the jobs related to its goal, all automatically. Which means a true robot doesn't require a human controlling exactly what it does. In general, the field of robotics also deals with machines that do all of the same things, but might require a human operator to carry out some tasks. Whether fully automatic or not, virtually all robots have a few features in common. First, robots are machines made from materials that occupy physical space, so they're more than just lines of computer code. That's one of the key features that distinguishes them from AI, although computer engineering is important for robots as well. Second, most robots have some way of sensing features of their environment, usually by measuring light, sound, or force feedback. They can then use that information to make a decision about what to do next, depending on what they're designed for. The tasks robots are built for tend to be complex, requiring a sequence of different motions. So an automatic door that opens or shuts in response to whether you stand in front of a sensor wouldn't be considered a robot. The tasks that robots handle are more sophisticated, like welding two intricately shaped pieces of metal together. Third, to interpret the signals they receive from their environment and coordinate some sort of response, robots have computers built somewhere into their design. These work just like any computer, taking inputs and delivering outputs. But unlike most ordinary software, the software on a robot's computer generates electrical signals that are directly passed onto the robot's hardware, instead of just changing information in a file or on a screen. That also requires a power source. One option is to physically hook up to the power grid using wires and a socket. For example, the 2013 version of the Atlas robot, developed by robotics company Boston Dynamics, had a humanoid design that could walk and carry objects much like humans do. To operate, Atlas relied on a cable that tethered it to a power supply. But tethering robots like this limits how far they can move and interferes with the robot's mobility. So to let Atlas move around more freely, engineers installed a battery on the robot's structure so it could power itself. Unfortunately, the materials of a battery tend to be rather heavy, which posed its own challenges. If we don't want robots like these toppling over all the time, it takes a bit of mechanical engineering know-how to work out where to position the battery with respect to the robot's centre of mass. You might need some chemical engineering in the design of the battery too. In the case of Atlas, engineers gave it a hydraulic pump in its torso to help it support the extra weight of its lithium-ion battery. And now, only a few years later, it can do backflips and parkour. More generally, some electrical engineering also has to go into wiring the signals from the computer program to the robot's physical parts. Which brings us to another common feature of robots. They have mechanical parts like grips or wheels for carrying out whatever physical task they need to in their environments. That might be turning a lever, picking up an object, or just moving somewhere else.
Pat, you're on mute.
Yeah. Unmute.
Yeah, guys. Thank you.
Someday in the near
Sorry, that was a great video giving us a different aspect of lots of different engineering disciplines that go into a robot. What we're going to focus on today is the coding aspect of it and to get you comfortable, hopefully, with how that works. And so one of the things that you need to think about when you're trying to write code is, what do you want your robot to eventually do? And our robot, in this case, is going to be a little sprite on the screen that's going to do whatever you tell it to do. Turn right, turn left, go forward, go backwards. But at some point, you may want to sense, where it's going, plan, and then act. And so the sense might be, am I on a black piece of the screen, or am I white? Is there something, if you have a distance sensor, an ultrasonic sensor on a real robot, you might sense where you are with respect to a wall, and then plan to turn, and then go ahead and act, and then reassess when you do that. And that's how you can maneuver your way through a maze. So we'll give you a brief timeline here, because I do want to get into, how the M-block coding works. And so, you can see here that the coding timeline has come a long way from mechanical computers, and Alan Turing, and all the way up through, what we have now in terms of all the various coding languages and the platforms, and how quickly we can process things. And so it's been quite a journey for 100 years. So one of the things I want to just do an experiment with you a little bit is, if you have a piece of paper in front of you, I want to quickly go through just an idea of instructions. So if I tell you to draw a circle in the middle of your piece of paper, hopefully you have something you can think about. You can draw that circle. Then I might ask you to draw a triangle on top of it. You can think about this in your head, or you can draw it out. I might ask you to draw a squiggly line on the left, and maybe a rectangle on the right of that circle. And you're imagining what it might be, and you may draw it out, but I'm curious to see if it looks anything like that, right? And I didn't finish the instructions, but what I'm asking you to do may turn out to be different based on, maybe I was a little vague, and what size rectangle, how big of a circle, what kind of triangle, how was it oriented? So being specific in your code is going to be a really huge advantage in you being able to be successful here. So what I'd like to do is get into the process here, but also I need to show you how M-block works. So the idea is design, think about what you want to accomplish, and then write it in small chunks. If I were to give you one piece of advice, don't think about doing all of it at once, because that's not what programmers and coders do. They do a small amount of debugging. All right, they write a little bit of code, see if it works, write a little bit more, see if it works. So test. When you're doing this with your sprite, have it do small little segments of movements and see if it works, see if it's behaving the way that you want it to, because then you can make your small adjustments, and then as you go forth, what you just did is the way that you want it to be. And so small chunks as you design, code, recode, and identify any issues, and then continue that process. So hopefully that's a habit you can get into. It is interesting, the idea of debugging. That was something that when they had punch cards for coding, and there was little holes that dictated the code, and a moth got stuck in there. So that was the beginnings of the idea of a bug in your code, a literal bug in that case. Okay, so we're going to get into loops and variables and conditionals, and I want to spend a little bit of time just getting into it. And so so what you'll do is, if you have access to a computer right now, you can follow along with me a little bit, and we're going to get into M-block and then get into coding with blocks. And so I want to show you this platform. And so hopefully you can get comfortable with it. Loading a little bit. So you can see here, there's lots of categories on the left-hand side for types of code. But if you go to the left menu, you're going to want to go to sprites. And so you can choose your sprites. I'm going to stick with the panda because they're kind of cute and I like them. And you can make it do different things. So in this window here, this is where the panda is going to move. And what I would recommend, you may want to click on the far left here. And if you want to change your, let's see here, any characteristics, you can do that. And I think I stopped sharing. Share. Sorry about that.
No worries. And we can see your screen, Pat.
Oh, can you? All right. Then there we go. I popped out of my window. Thank you. So I need to get out of this window. Okay. So what I turned on was the grid, and that's going to be kind of helpful sometimes, because you can see negative 100, positive 100. You can start your panda wherever you'd like. And so let me show you a little bit about the buttons here. You see here events. And this is going to be the one that you're probably going to want to use, because when you click the little green flag over here, that starts the code running, and it always runs top to bottom. So when you want things to happen, make sure you put it in that order, top to bottom. And so I'm going to move my, I'm going to have an event, right? So event might be when clicked. Control is what do you want it to do? And then there's also motion. So control is controlling here conditionals and things like that. So if the panda runs into a wall, or if it moves 10, then turn right and do different things. So those are conditionals. But let's start with the basics of motion. And so I can move my panda 100. And then you may want to say, well, after that, let's turn. And let's turn 90 degrees. And then move again 100. Now you can actually right click and duplicate these if you want to work it out that way, to get as you want to move a little faster. But I'm just going to show you different basic motions, and then you'll have time to play with it. Now, this is where I may want to test, see what it looks like, right? So I'm going to press green and watch what happens. It very quickly moved to the position, 100 over, 90 degrees, 100 over, and then turned. It happened very fast. So if you want to maybe see what you just did, you may want to use a pen. Now, and that's something that you may need to add. So this is what I wanted to show you. If you go to extension down here, all the way at the bottom, and you want to add an extension, it gives you selections. And you go to pen, and you want to add that. So this is something that you may not have if you haven't used it before. So as you go all the way down, move my own menu here. The zoom menu, get out of the way. All right. So I'm going to go to pen all the way down at the bottom there, and it gives you choices. And so I would like to, sometimes you want to erase all in case you do a lot of this and you have pen marks that are on there. They're not going to erase unless you say erase all. And then you go pen down. And so it does that first. And let's get that 100 steps there. So now what's it going to do is I want to reset it. I can reset it at a different position, but I'm going to start where I am, upside down, and then I'm going to move 100, turn, move 100, and then turn. Let's see what we make there. Okay, so we made little 2 lines that are 90 degrees apart from one another. Well, maybe you want to make a shape, and this is one of the challenges that we're going to hopefully get you through today, and you get creative with your shapes. So maybe I want to move 2 more times, right? And so if you press that, then it's hard to see, but you made a little square there, okay? So you get if you look at this though, this is an interesting way to code. Now, one of the things that as you get more experience with coding, you want to make sure that you streamline what you do. And so here we have sets of steps that are repeated, right? Move 100, turn 90, move 100, turn 90. Well, what if we wanted to kind of condense that a little bit and say, well, if we're repeating something, is there a function that we can use to repeat the same thing over and over again? And so if we look at control, well, there is, isn't there? And we can repeat, we can wait, we can do if then. And in this case, we go down here, repeat a number of times, I think would be a way to help us do this. Now, if we're trying to make a square, and then you would say, well, I have 4 sides of that square. And so let's repeat that 4 times, right? Move, turn, move, turn, move, turn. And so you can accomplish the same task, but in a smaller amount of code. And I think that's something that we can hopefully strive to do to be a little bit more efficient. And so as we go further, I just want you to be aware of all the operators here, and you can do random numbers. And so maybe I want to make something that isn't 4 sides, but maybe I insert a random number. And this is something I want you to explore, okay? Hopefully you can have some fun with this. And so variables are going to be a key, and that's something you can do down here. Make a variable, and maybe, just maybe, you want to make different shapes. And you know that different polygons have different number of sides, from 3, 4, 5, 6, 7, 8. So maybe the number of sides is a variable that you want to use to help randomly make different shapes. Okay, and you can do different things with that variable now. And you can also display it up here. So hopefully as you explore MBlock, you can see all the different things that you can accomplish. Now, I know we want to get you going with this with this fun activity. And so there are instructions here that are in the lab. Hopefully you're kind of following along a little bit as you go. And you can save your work. And so don't forget to throw a title on there. I didn't throw a title on there, but I can say intro maybe. And intro 1, or I can call it a shapes, different things like that. So make sure that here are the things that I want you to focus on. The functions, what are you doing? What actions are being taken? And then, you know, what do you want to do? And so do it in small chunks. I'll remind you again, 3 or 4 lines and see how it behaves. And so that, you know, that's kind of quality control. You can figure out as you go further how to add more to it. Now, drawing shapes here, like this is something I just did with you. And, you know, hopefully you can take that large chunk of code and you can put it in loops. You can repeat it. You can do it forever and just keep on going and going. And look, that forever loop is an interesting one, because if you're going through a maze, you don't know how many times you want to turn and look and check. And so it could be 20 before you get out of that maze. It could be 100. So you might want to do this forever loop just to continually check. It's like you walking through a room trying to figure out how to get through a store or a mall. You don't have a limit on how long you're going to keep looking and moving and seeing where to go. You just keep checking and checking and checking. So that forever loop can be very helpful in those cases. Variables are going to be helpful. Maybe you want to do a shape or maybe navigate through a maze for a certain amount of time to see where you end up. And so making that variable, I showed you a little bit of that before. And this if statement, this is interesting too. And I want to take just a moment to show you how you might apply this. And so if you look at the pond here, this is something you might have some fun with. You can add this background so that your sprite is moving around. So maybe your panda is swimming, or you can change your sprite to a fish. But you can do you move forward, and if you cross over from blue to beige, then turn, or move backwards and turn. And so it's a conditional. Under certain conditions, you change your motion and make things happen. And hopefully your robot, or sprite in this case, will navigate to where you want it to navigate. So hopefully you guys will have a chance to do the maze challenge. And to make the maze, just so you know, you're going to have to draw it in the background. So you click on background and draw thick lines. So if that's something that you struggle with, please ask us in the breakout rooms, and we can show you a little bit how to do that. And so you can make your own maze and be super creative with it, and then see if your sprite can make it through. Okay, and you can do it through very deliberate movements: move forward, turn. And in some cases, you can do a random. You can keep bouncing around the room until you make it out. And that's up to you. Have some fun with it. Be creative. And that is the wonderful thing about coding, is that is one of the greatest things you can be creative with. You can make as little or as much as you want to when it comes to movement and what the code is accomplishing for you. So I do want to get you started on that. So as a reminder, a little recap. You want your bot to sense, plan, and act. And so think about what you wanted to accomplish. Do small chunks of code to make that work. And I think at this point, I would love to let you guys get started. And so, Jillian, are we back to you?
Possibly? Yes. What an amazing introduction. Oh my goodness. Sheesh. You're the best kind of teacher. You showed us, didn't just tell us, you showed us. And I could really use that robot that was folding clothes, Pat. We'll talk about that. Well, you guys, it is time for you to get to work on your lab challenge. We will open the breakout room for you, where ET staff and college mentors will meet you there and guide you along the way. When we come back, we'll have our Q&A and wrap up. We can't wait to see what you've done and hear all about it. So meet you back here at 11:30. See you then.